Let's get this show started. Hello, everyone.
Hey.
Great to see you again. Hope you're well. Let's jump into it. So, well, I guess before I share my screen, maybe I should just do a bit of important recap for those who might have joined the class late. I believe I got a couple emails. So, for those of you who were attended the first couple of classes, this is nothing new, but anyone just joining us, some important pit stops is to go to our class webpage. So you go to just Google CCNY Math or whatever, click on any link that will take you to that website. And of course, it's a little bit slow to load. Go to People. Then you can find my name all the way down the bottom. Last name is Smith. And that will take you to this page over here. And then you can click on the link to the class under Summer 2020 classes. You can go here. By going there, you will find a lot of important information that you will be referring to throughout this semester, however long that is. So of course you can find the syllabus here, where all the links are clickable, and that's our class webpage. That's very important. And okay, so that's where you find the syllabus, all that important information. If you go back to the website, you'll find the course learning outcomes. Links to the videos are posted here. You can click there. It will take you to the YouTube playlist where I have been posting the videos. As you can see right now, that looks like a duplicate right there. I'll remove it. But as you can see right now, I don't want to do anything now and do anything by mistake. As you can see right now, there are really 2 lectures that are up. That's just a duplicate for some reason. And if you click on the lectures, you will also find the notes of in the video description. So if you click there, you will find the PDF version of the notes for the class, as you can see here. So, okay, so that's just double checking there. You should make sure that you can actually access the homework. That's going to be very important. All that stuff was covered in lecture 0, quote unquote, which you can, if you are joining the class late, whether you joined on Tuesday or you're joining today, you definitely want to go back and watch lecture 0. A lot of important information was given in lecture 0. In addition to that, there was a questionnaire that I asked you guys to do. So if you did not do that, I would encourage you at this point to do that. Not only will this help with, so let's see here. Here's the link to the questionnaire. So if you didn't fill that out already, fill it out. Otherwise, I post the link in the chat. Please fill out the questionnaire. I will cross-reference that with the registration for Zoom to take attendance. I have to officially submit the attendance roster on June 1st, so I need to make sure that you're actually attending. So fill out that questionnaire if you haven't done so already, and yeah, we'll move on.
How do I take my attendance, by the way?
Hello?
How do I take my attendance?
You don't take your attendance. I take your attendance. Make sure you fill out the questionnaire, and make sure when you register for the Zoom meeting,
I already filled out the questionnaire.
Yes. Jason, you need to listen. Jason, listen to what I'm saying. If you have not done so already, fill out the questionnaire. You can only do it once. If you've done it already, just ignore what I just said. This is for, I'm making announcements for people who are new to the class. Okay? All right. Because students are still joining. I have students joining the class who were not here. So everything I'm saying now have been said before. If you were here in the past 2 classes, you would have done everything I asked you to do already. And I don't know what Iftihar means by I look familiar, but whatever. Okay, so as usual, I'm going to turn off my video now and we're going to get into the lesson. And so now, oh, okay. So apparently you watched my videos for a previous class and you're like, where did I see this dude before? Like, why does this guy look so familiar? Okay, yeah. So I have lecture series for a bunch of courses that I've been teaching, going, I don't know, way back. I have lecture videos for things I taught back in spring 2014, I think. They go way back. Anyway, that's where you would find the lectures for this class. Now, just a small recap of what we covered last time. We spoke about basic integration techniques, essentially basic forms that I expect you to remember. Those were here. Just a recap. We also started talking about integration strategy, the first 3 things that you should think about when faced with any random integral, what you should be doing. The third thing is always substitution, which is what you learned at the end of Calculus 1. The fourth technique we are going to teach you, which I already kind of taught you, is integration by parts. That is using this formula to compute an integral. It's actually the reverse of the product rule. So we did that and we did a bunch of examples. We found out how we would choose the parts in integration by parts. This is using the mnemonic Leotta. So Leotta tells you who to choose to be the u. Guys, the type of function that's more to the left in the list of Leotta is the guy that you would choose. It's a guideline. It does not cover all possible situations. But if you have 2 different kinds of functions being represented in an integral and you feel like integration by parts is going to be a useful tool, then Leotta will be how you would choose it. There are situations in which you would do integration by parts, but Leotta won't help you. For example, if you have 2 of the same kinds of functions being mixed together. And there are times when integration by parts would work or integration by parts will not work. We'll see examples of that moving forward. But once we get more techniques and more experience under our belt, we'll be able to use this method more effectively. We saw examples that were pretty straightforward. You do integration by parts once and you can get to the answer. We also saw examples that were a little bit more complicated, where we started integration by parts and we got back the original integral that we started with. And we learned that the way to deal with that is just to expand the parentheses, bring the integral you want to solve for on one side. And yeah, that you can figure out. We also saw situations where we do integration by parts and we have to do it multiple times in order to get to an answer. For this, of course, our algebra needed to be on point. We needed to make sure we're using our nested parentheses very effectively and so on and so forth. And that itself presented some challenges. So for example, there are times when you see an integral like this, where if you're looking at that, you would notice that you have to do integration by parts 5 times in a row, which will be a lot of parentheses, a lot of algebra. And so we were like, nah, there's gotta be a better way. And there is, it's called tabular integration. And we kind of ended the class there. As well as I gave you some more examples to try. Hopefully you guys actually tried these. You didn't really need anything as sophisticated as tabular integration to do them. So hopefully you guys actually tried that. We will get to that. But before that, I do want to teach you guys about tabular integration so that if you're ever in a situation where it would be needed, you know how to do it. Then I will go into these examples, which I asked you guys to try, and we will take it from there. And if we get through all of that in today's class, we will move on to starting 8.3, I want to say, which is trigonometric integrals. Okay, I do have some comments in the chat, so let me make sure that there are no questions. You don't mark yourself present in the class. All you have to do is just register for the Zoom lecture with your full name to answer that question. Okay, all right. Oh, that's nice. Some people already responded to the questions. So that's good. Help each other out whenever you can. And let's move forward. So we will get to these examples in a bit. For now, let's ignore them. I do have copies of them written down here. Okay. And yeah, so let's actually jump into it. I think there's a better way. It's called tabular integration. So I'm going to now teach you guys about tabular integration. Which is going to be really cool. It's like a way to streamline integration by parts, do integration by parts repeatedly in a manner that won't get you lost in a sea of parentheses, and it would reduce the likelihood of a mistake. So I had the notes over here. So let's do that. Boom, 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 boom. All right, so let's talk about tabular integration, right? So again, tabular integration is, hold on, another comment. Okay, awesome. Okay, so tabular integration is, again, it is integration by parts. Technically, it's not a new technique. It is just a way to streamline a technique that we already know. So if you know integration by parts, tabular integration accomplishes the same thing integration by parts accomplishes. However, it can be a little bit more easier to implement for situations where you have to repeatedly use integration by parts and you don't want to have to worry about parentheses as much as you had to before. I will also say that tabular integration is something that you can use in every single situation where integration by parts will work. So if you like the tabular integration way, you can do this method all the time. It will work in every situation where integration by parts would work. Some people like to reserve it for the more complicated situations, and they just do integration by parts by the formula as routine. But if you really like tabular integration, you can do every single integration by parts problem with tabular integration. So I'm going to go over that. I'm going to teach you how tabular integration works. Then I'm going to actually redo a couple of the examples that we've already done so that you can see how to do them. And then I'm going to do the really long problem that would take 5 integration by parts, but we're going to do it relatively quickly with tabular integration. So here's how tabular integration works. So suppose you have an integral that looks like this. There's a big f of x times a big g of x, right? And you want to integrate that using integration by parts. So again, you apply this when you want to do integration by parts. If you would set the f to be the u and the dv to be the g, here's how things would be set up, okay? So I'm going to show you, you would actually, it's called tabular integration because what you're going to do is you're going to set up a table. So we have the integral of f of x times g of x. And this is something that I noticed that I want to use integration by parts with. However, maybe it's just complicated. Below that, you will immediately draw a table. Okay? And then, everything I'm going to say verbally here, I wrote it in words here, so you don't really have to take notes on what I'm saying unless you want to. But I explained here how you fill out the table and how you know how big the table is. So right now you can just follow along with what I'm saying. Here's what you're going to do. So you know that you're going to pick the u to be this guy and the dv to be this guy. Remember what you do with the u, you differentiate it. So how you fill out this table is that you keep differentiating the u. So you would differentiate that 1 time, you differentiate that 2 times, ... You will differentiate it n times, however many times you will need to differentiate it. Then, secondly, for the dv, you'll keep integrating. So for the second column, you just repeatedly integrate this function. So you integrate g, and I'm going to use the notation of the subscript. So g subscript 1 is the first antiderivative, g subscript 2 is the second antiderivative, ... going all the way down to g subscript n is the nth antiderivative. Now, once you actually do that, you can now start to figure out the pieces to go along with this. So what you're going to do now is you're going to multiply along the diagonals. And then to end the process, you're actually going to multiply across the last row. On top of that, there is some sign changes that go along with this. So for the first one, you're going to apply a positive sign to the product. Second one, you're going to apply a negative sign to the product. For the third, you're going to apply a positive sign. You're alternating the signs. And what this is, it's basically, remember when you have the integration by parts formula, there's a negative sign inside of it. So once you open parentheses, that negative sign is going to change all the signs inside the parentheses. And it turns out that it will keep alternating, right? So eventually, once the negative sign comes, or again, on the inside of the parentheses, it's going to change the negative to a positive, and so on and so forth. So you'll have signs starting to alternate. Now, in the final situation, it depends on how long the table is. There's going to be a plus or a minus sign here. You have to kind of figure out, it depends on how long, whether you have an even number or an odd number of rows, okay? But now notice that you'll have these products. You would have f times g1, f prime times g2, f double prime times g3, etc. Going down to f to the n minus first prime times gn, and then finally you have this. Now, you put these together in the following way. This integral, the integral of big F g dx, is going to be equal to, you're going to take these products and apply these signs. So it's going to be positive f times g1 minus f prime times g2 plus f double prime times g3 minus ... You alternate signs until you get to the last one, plus or minus. And then the last term is going to be the f to the nth derivative times g sub n. But this last term, you're going to do an integral, right? So that is the integral that is in the integration by parts formula. That is the last integral here. Where did I have that formula? That is this last integral here. So at the end of doing a bunch of repeated integration by parts, what's going to happen is by doing repeated integration by parts, you're going to have all these terms, and then they terminate in the final integral for the problem, okay? And it turns out by doing this integral, by doing this computation here, it's the same as doing that integral. And so it's actually a lot easier. So I'm explaining this in theory, but we're going to do a concrete example, okay? And that's how you put them together and you obtain this formula. So what you can think of this is a generalized integration by parts formula. And instead of memorizing that formula, what you can do is you can build this table to actually figure it out, okay? And so one thing is, let's see some comments here. Okay, so here's a comment here. How do you know when to stop? This is a very good question. And here's the answer. The table terminates when one of these three conditions are fulfilled, okay? So obviously here, I just drew a table that has n rows, but you might be guessing, well, how do I know what n is? How many times do I go through this, right? So here's what we're going to do. There are three situations that you know when you would stop the table, and I'm going to show you examples of all of these. One, if the derivative column eventually hits 0. So if there comes a point where you keep differentiating and you hit 0, this of course happens if your big F is a polynomial, at some point you're going to hit a 0. At that point, you would stop the table. You would stop when you hit a 0. That's one situation. Another situation is if you realize that the product along a row is going to be easy to deal with. So if you're in a situation where it never hits 0 in the left column, however, if you read a row, you realize, you know what, if I were to multiply across, that's an easy integral to deal with, easy in quotations. you can stop the table then. That's the second scenario. The third scenario is whenever the product along the row becomes a constant multiple of whatever the original was. So if there comes a point where if you read across the row, you would get a constant times the original function, then you would stop the table then. So these are the three scenarios. When you hit one of these scenarios, this is when you stop the table. Okay, so let's do an example. I don't know if I should do this first. Okay. Let's do this one first. Okay, so this is an example that we already did, right? We did this with regular integration by parts. It was a very short problem.
Actually, this problem.
Let me do the other one.
The tabular method. What you can do is just
example.
Regular integration by parts. Now, you pick like
x cubed e to the x dx. That was also one that we did. You might have remembered that one. Okay, so here let's actually let me show you how to actually do this method from scratch. So just watch me, and then we'll cover some other situations. So this is a situation where we have pretty much case one is going to occur. Okay, so we see this integral, right? And again, we're going to go through the strategy in our heads. We're going to be like, okay, step one, is there a basic rule for this integral? No? Okay, step two, can I simplify to apply a basic rule for this integral? No? Step three, would a substitution work? No, right? You'd run through all those in your head. You always run through those three things every single time in that order. Okay, once you realize that those three things aren't going to work, now you have to look for a different method to try. Of course, integration by parts is the only other thing we know. So we know that integration by parts is what we want. Once you do that, you need to know how to choose the u and the dv. By Leotta, we know that the u is going to be the x cubed and the dv is going to be the e to the x. Now what I'm going to do is I'm going to use the tabular integration method to actually figure this out. So here's what that would look like. I would draw a table below this. And in the u column, I would keep differentiating. The derivative of x cubed is 3x squared. The derivative of 3x squared is 6x. The derivative of 6x is 6. And the derivative of 6 is 0. Now, once you see that, you see this hits 0. Notice that that covers case 1. If the derivative column eventually hits 0, here's where that happens. Now, once that happens, you stop. Right? That is telling you that the table that you need here needs 4 rows. Once you know that, now, okay, this is when I stop this table, you go to the right column, and now you keep integrating. So integral of e to the x is e to the x, integral of e to the x is e to the x, integral of e to the x is e to the x, integral of e to the x is e to the x. And so now what we're going to do is we're going to multiply the products. X cubed times e to the x.
We're going to use the arrows, like, you know, from 3x squared times
3x squared to e to the x.
6x times e to the x.
Yes, Jason, I'm explaining. Please be quiet. So now you would multiply along these diagonals. X cubed times e to the x, 3x squared times e to the x, 6x times e to the x, 6 times e to the x, and then you would multiply across here. Now notice here, the multiplication across here is going to be 0. So that last integral in the formula is just going to end up being a plus c. Also, we apply the signs. So there's a plus sign that goes with the first thing. There's a negative sign that goes with the second thing. There's a plus sign that goes with the third thing. There's a negative sign that goes with the fourth thing. And so there's going to be a positive sign that goes with the fifth thing. And so in this case, if this integral is I, at this point, I would be able to say that I is positive x cubed times e to the x minus 3x squared e to the x plus 6x e to the x.
I have a question. How do you get from positive to negative? Can you explain that for a little bit?
Come again?
For the positive and negative signs, how do you get that? Can you explain that for a little bit?
You always start with a positive and then you alternate. And where that comes from is when you're trying to apply integration by parts repeatedly, right? So remember, if you did integration by parts, what would you have? You'd have a u times v minus the integral of v du, right? And so let's say this is the first integration by parts. Then if you want to apply it a second time, you'd have a u2 v2 minus the integral of v2 du, right? Then if you wanted to apply integration by parts a third time, you open a second parentheses, and then you would end up with a u3 v3 minus the integral of v3 du, right? Now what you'll notice is if you were to expand all this, right? If you expand this here, you would get a u1 v1 minus u2 v2 plus this integral. And in this situation, you would get a u1 v1 minus u2 v2 plus u3 v3 minus this integral. So notice what's going on with the signs. They are alternating, right? You start off with a plus, then you get a minus, then you get a plus. In the next situation, you start off with a plus, then you get a minus, then you get a plus, then you get a minus, right? So this is just a pattern. Like if you were to write out the integration by parts, you'll notice that this pattern is occurring. It alternates between pluses and minuses, right? So that's what these signs on the arrows are meant to model. These signs are going to alternate anyway, right? And so we know that that's the pattern that we're trying to get. And so that's what this table is doing. That's why we alternate. You always start with a plus here, then minus, then plus, then minus, then plus. You keep alternating. Once you do that, you write down, take all these products, apply the signs, add them all together. Finally, you're going to end with a 0 dx, which we all know that integrates to a positive c. And so we get that the answer, integral of x cubed e to the x dx, is x cubed. And x cubed minus 3x squared plus 6x minus 6. All of that times e to the x. Jason's going to be very happy with this. We're finally being able to factor something. Because here it actually is nice to factor because it saves me from writing down a lot of stuff. And that is the answer. And of course, if you look back in your notes, you'll notice that that was the answer that we got last time. Right? So you'll notice here, and again, once you get used to this, I'm explaining everything, so it took a long time to get through this problem. But trust me, this was much quicker. When you get used to this method, it would actually be much quicker than doing it regular integration by parts. It's much quicker than doing all of this here, right? You'll be able to set up a table pretty quickly and get to an answer pretty quickly. In fact, let me do the other one. Let's do the guy that we were afraid of. Now for this guy. X to the 5th e to the x. Last time we were like, nah, not going to waste my time doing that because that is just too much work, right? But notice with tabular integration, it's actually not too much work. This, how would I do that? Well, I start drawing a table. Keep differentiating. 5x to the 4th, 20x cubed, 60x squared, 120x, 120, 0, stop, integrate, 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 integrate. Then multiply, 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 multiply. Then you just, of course, you know to apply different signs. And you can write this down if you want, but in your head, you'll know, okay, now you can just read them off. It's a positive x to the fifth e to the x, minus 5x to the fourth e to the x, plus 20x cubed e to the x, minus 60x squared e to the x, plus 120x e to the x, minus 120 e to the x, plus c. That's your answer.
Oh, look, it's actually 60 for x squared e to the x, not
60
20,
where?
actually. 60 x squared e to the x, not 20, actually.
Yes.
Because according to another
Jason is out here keeping me honest. So that's the 60. But yeah, now, of course, you guys can imagine, and that's the whole problem. Of course, you guys can imagine, if you were to do this directly with integration by parts, how long that would have taken, how many parentheses that you would have to expand and all that good stuff. And it would take you a really long time to write it out. But yeah, it's like, it'll take you 10, 15 minutes to do that and making sure you're not dropping the signs. However, with tabular integration, that was fine, right? Okay. Yeah, it's a really nice method. And unfortunately, it's not taught very often in Calculus 2. I don't know why. I learned about this method after I already passed Calculus 2. So I don't know. But it's a very efficient method. It can really save you a lot of time and a lot of headache and a lot of making mistakes by expanding parentheses and forgetting to change a sign. Okay? All right. Glad you guys like it.
Are you saying to use this for every integration problem that we occur?
No. Any integration by parts problem, you can use this. Okay. Okay. So now let's do some other problems. Here's where is the other guy? Okay. Let's redo a couple of the problems that we already did with this method, so you'll be convinced that it can work in every situation. Here was another situation, right? This was a very short situation. Literally, integration by parts one time is going to get you the answer. Let's look at that with tabular integration. So here's another example, right? So this was our integral, the integral of x squared ln x. Okay. Maybe someone can suggest to me what to do here.
You would start out by making a table.
Okay, so just start drawing it right under.
Yeah.
Okay.
And then you would start differentiating the left side.
To get?
Which you get 2x, 2, and then 0. And then you would integrate the right side.
Okay, what's the integral of ln x? No, the 1 over x is the derivative of ln x. Okay, so we're in trouble here. And at this point, some of you are probably like, what? Jhevon told us this is going to work out. Now, hold on there. You are actually applying tabular integration incorrectly. Does anyone see the mistake here?
You have to use the mnemonics.
The Leotta method?
Leotta. Remember, once you're doing integration by parts, the first thing you have to figure out is who is the u. The u needs to be on the left. Now, in this situation here, Leotta says the u is going to be the ln x, which means this is not what the table should look like. So be careful.
Will be first.
So the first thing you would do is you would rewrite this in this order, then do the table. Now the derivative of ln x is 1 over x. The integral of x squared is x cubed over 3. What you'll notice now is that this is an example of case, I forgot what I numbered it because I did these notes a while ago. This is case 2. The product along a row is easy, quote unquote, to deal with. What you'll do here is realize that no matter how much I differentiate, I will never hit 0. So now I'm starting to look for something else. Either I'm looking for a row to give me back the original with potentially a constant factor, or I now know that once I differentiate an ln, I'm never going to get an ln back, so it's definitely not that case either. So what I do now is I wait until I see a row that if I multiply across that row, I know how to integrate that easily. Now, if I multiply 1 over x by x cubed over 2, that gives me x squared over 2. That's easy to integrate. So what I would do here is stop, because this is case 2. Now I would multiply here, take a plus sign, multiply across here, take a negative sign. And so in this case, the integral is going to look like x cubed over 2 ln x minus, remember this last one, you apply an integral to it. This should be over 3. And now what you'll realize, that's over 3. This here now is just 1/3 x squared. And so you would get this here, x cubed over 3 ln x minus x cubed over 9, which again, if you look back in your notes, was the answer we got back last time. Now in this situation, writing out integration. Yes.
Can you go back to the case number 2?
You mean the written?
Wait, can you go down?
Yes.
Yeah, this part. 1 over x. Why did you not differentiate that?
Come again?
The
1 over x is the derivative of ln x.
Oh, okay.
Right? So you differentiate in the left column. The derivative of ln x is 1 over x. Now at this point, I would stop. And the reason why you would stop is because I noticed that you keep going until one of these 3 things is fulfilled. And after doing 1 time, the second case was fulfilled, right? Multiplying across here gives me an easy integral to deal with because that's just the power rule. This is not a situation that it would ever hit 0. It's also not a situation where I would get back the original after some point. Yes, that's correct. ln will never hit 0, right? If you differentiate ln, you get x to the minus 1. Differentiate that, you get minus x to the minus 2. Differentiate that, you get positive 1/2 x to the minus 3, right? You're never going to hit 0. You're just going to keep increasing, you're going to keep decreasing the power of the x by 1, and it's going to skip over 0, right?
Oh, so you just multiply.
Right, so yeah, so this is a situation where we're never going to be in case 1. It's never going to be 0. So if you keep differentiating trying to hit 0, you're going to be differentiating forever. So I realize here that this is not case 1, which means I'm either in case 2 or case 3. I also know it's not case 3. How do I know it's not case 3? Because I need to have a constant multiple of the original. The original has an ln in it, right? Now, once I differentiate and lose the ln, there is no derivative that's going to give me an ln back. So I know it's not case 3. So now I know, just by me knowing about the function ln and how its derivatives behave, I know for sure I'm in case 2, which means I'm just going to go row by row until I'm in a situation where multiplying straight across a row is an easy integral to deal with. And in this case, that happens on the first row, right? Now in this situation, clearly tabular integration works, but to me, it's kind of overkill. You could do it, but I would rather just do the regular integration by parts. But of course, it's up to your preference. We did this example last class. You can go back and compare the two methods and just decide, you know what, I like the tabular way better. I'm always going to do tabular, and that's perfectly fine. You can also have a situation where you might do sometimes tabular, sometimes not. That is also fine. You might also be the person who's like, I'm not into this tabular integration thing. Let me just do it the regular way and multiply out parentheses. That is also fine. I'm just showing you a bunch of different options. There are situations in which tabular integration is a lot more faster and a lot more efficient. For example, with this example. This is not something I'd want to do in the regular way. I would definitely do tabular integration here, but again, that's just me. I don't want to spend forever doing algebra. Something like this, I would probably do it the regular way. However, if you wanted to do tabular, you can still do it. Let's redo this example. This was a weird one, right? This was the one that was a revolving integration by parts. This is one that when we did integration by parts, eventually we got the same thing back, right? So let's see what that would happen. It turns out that that is case 3, right? So here I have sine of x times e to the x. I would start to write out the table. All right, so now the derivative of sine of x is cosine of x. The derivative of cosine of x is minus sine of x.
Professor, do we have to check the Leotta thing first?
Yes, you always check the Leotta thing first.
Okay, good. Okay, gotcha.
Right? Once you know you're doing integration by parts, the very first thing you have to do, whether you're doing tabular integration or not, is you have to check Leotta, right? So by this, according to Leotta, the u would be the sine. Right? So so again, to go back a little bit more when it comes to what we were talking about. Whenever you see a new integral, again, there are certain things you want to think about in a specific order, right? You don't want to be in a situation where you're looking at an integral and you don't know what to do. Oh, I'm kind of lost. I don't know what to do. That should never be a situation that you're in, not in a Calc 2 class. You see a random integral. The first thought that comes to your mind should be, is there a basic rule that covers this case? The basic rules are the guys that I gave you guys in the table early on, these guys. Does one of these rules cover what I'm looking at? If not, the second thing you think is, can I simplify so that one of those rules cover what I'm looking at? The third thing you think, if that doesn't work, is, will a substitution work? Can I set u equals something that will give me a beneficial situation? Now, that is always what you think, the first 3 things in that order every single time. Every time you see a new integral, you think of those 3 things in that order. Now, once you realize that those 3 things would not work, you would want to choose some other method. Now, so far, there's only one other method we know about, so obviously it's going to be integration by parts at this point. But later on, when I teach you more methods, I'm going to tell you how to pick and choose which method. But for now, let's say you choose integration by parts. Once you have chosen integration by parts, you need to choose the parts, right? So if you review what we did last time, when we did integration by parts, the first thing I needed to do was figure out the u and the dv, right? Once you know, okay, integration by parts is my approach, then you have to know u and dv to apply integration by parts. How do you know u and dv? Leotta. So yeah, once you decide integration by parts, the first thing you're going to do is Leotta. This is assuming you already went through the first 3 steps in the strategy. Once I realize Leotta, who's the u, now if I decide, okay, I want to do tabular integration, put the u in the left column, and then you continue. Now, what that would mean in this situation is that I put my sine of x in the left column, and I keep differentiating. Then my e to the x is in the right column, and I keep integrating. Now, what you notice here about this last row is that this is -1 times the original integrand. Right? The original integrand is e sine x times e to the x. Here, I have negative sine x times e to the x. That tells me I'm in case 3, which means stop. Right? I realized that I got to a row where I have a repetition of the original integral. It's off by a constant factor, but it doesn't matter that it's off by a constant factor. So once I realize I get the same thing back, I go through the process again. Multiply along the diagonals. Plus sine, minus sine, plus sine. Then I'm going to add up all these products. So I'm going to have a positive e to the x sine x, then minus e to the x cosine x. Then I'm going to have a positive, and this has a minus sine x, e to the x. But that, you will notice, is an e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x. Now what you'll notice is that this guy is the original integrand, right? This here is the original. This means bring to one side. Or in this situation, bring it to the left side. And ultimately, what you would get from that is that the integral of e to the x sine of x dx is going to be 1/2 times e to the x sine x minus e to the x cosine x plus c, which is, again, that's the answer that we got last time. So tabular integration even works on the revolving integration by parts scenario. That is just a case 3.
How'd you get 1/2 in front of the EX?
Okay, so that, I skipped some steps there because we actually did that yesterday. So remember yesterday when we did this example, I had the integral of e to the x is equal to, we had this equation here.
Oh, you brought the
When you
EX to the left
expand
side.
parentheses, you move it to that side, you get 2 of them over here, so you divide by 2, right?
Oh, okay, I got it.
So by bringing to the left side, just going through the algebra, you're going to see this 1/2 pop up, right? So that's
Okay.
included in bringing it to the left side. We looked at that yesterday. And to answer the question, no, the sign does not need to match in the original. Case 3 is you have a constant multiple of the original. That constant multiple could be positive or negative. And so, yeah, that's tabular integration. And now you see that it works in all scenarios that original integration by parts works in. However, there are situations in which it's much more efficient. For example, this guy, x to the 5th e to the x. That will take you forever doing this directly by integration by parts. But with tabular integration, it's actually no big deal. So I think that's pretty cool. And obviously a lot of you agree. But that being said, let's jump into the fun stuff. Yeah, we need a latte. Okay. All right, let's do these more examples. So I actually asked you guys to try these. So let's see what you guys came up with. So for these, you did not need tabular integration specifically, but you could have used it if you wanted to. So let me move these guys to the side. And we'll come back and grab them later. Let's make them a little bigger. Let's also make these a little bigger. Sorry, just bear with me here while I make this look a little bit nicer. Okay. All right, so here's where you guys are gonna chime in. Let me know what you guys did for these guys. Okay, so Natalie has a suggestion. Right, so here, this is an interesting situation. So here we have a situation where we just have the integral of a single function. In fact, this was a guy that I had asked you about earlier. What is the integral of ln x? Now we're actually going to learn what the integral of ln x is. Y'all gonna learn today. Okay, all right. So at first you might think, is this really an integration by parts problem? I mean, there's only one function here. Don't we need two parts to it? Don't we need a u and a dv? And the trick is, yes, we do need a u and a dv, but you don't have to technically be able to see both of them. There is, remember, you can always imagine that there is a 1 somewhere. So someone saw that you can think of this as ln x times 1. Okay, so a couple of people suggested that, and that was the thing. Now, of course, the ln x, well, that's an L. The 1 falls under A. So according to Leotta, the ln x is going to be the u, which of course that makes perfect sense here because it can't be the dv, because in order to find v, I would have to integrate. Even if I knew the integral of ln x, I wouldn't need to do integration by parts. So, right, the ln is going to be the part that you differentiate, and the 1 is going to be the part that you integrate. So for this one, even if you have a single function present, you can always think of a second function as being the function 1. So here I would say u equals ln x, dv equals 1 dx. So our du is equal to 1 over x, and our v is equal to x. Then we would have the integral of ln x dx is going to be equal to u times v minus the integral of v du. So u times v is x ln x minus the integral of x times 1 over x, so that's just 1. And of course, we know the integral of 1. So that is the answer. So in other words, the integral of ln x is x ln x minus x. Common mistake here, students just believe that they need to put absolute values around x's every time they see ln in an integral. This is not true. You don't put absolute values around the x here. It's just x ln x minus x. You could do the tabular method to check your work, as someone was asking. You could also differentiate to check your work. Yeah, there's a bunch of ways you can check your work. However, at this point, for this particular problem, you should not check your work. What I would like everyone to do at this point is memorize this. From now on, we will consider this as one of our basic rules. Knowing how to integrate ln is just something that we should all know by heart at this point, okay? From now on, we will consider this as a basic rule, okay? So when it comes to ln, If at any point in the future I ask you to integrate ln, I do not expect you to have to go through integration by parts, whether tabular or any other form, and figure it out. From now on, we all know what the integral of ln is. X ln x minus x plus c. Integral of ln x dx is x ln x minus x plus c. That's just something that we know now. This is a basic rule. The log function is a very fundamental function. It shows up often enough. It deserves to be something that is memorized. Okay, so this is more than just an example. This is one of our fundamental pillars of integration formulas. I'm just showing you where this formula came from. You can use integration by parts to figure out what the integral of ln x is. Okay, so copy that down, burn it into your brain, never forget. Okay. So yeah, so some good suggestions there. Let's do another one. So we do know the derivative of the inverse sine function, right? We know how to differentiate arcsine. By the way, what is the derivative of arcsine? Someone tell me. Derivative of arcsine. Are you guys looking it up?
It's 1 over square root of 1 minus u squared.
Well, 1 minus x squared, right? So it's 1 over the square root of 1 minus x squared. That is something I do expect you to know by heart. Okay, but in this situation, we want to find the integral of the arcsine. All right. Okay, I believe you, Natalie. You didn't look it up. I don't know if you can speak for everybody, though. I heard some pages flipping. Okay, all right. How did we do this one? Okay, thank you for the honesty there, telling me that you looked it up. But make sure you don't have to look it up again. It's something to memorize. Right, so u equals arcsine. Again, this is one of those situations where we think of this as, it looks like there's one function, but we can just think of the second function as 1. So then setting u equals sine inverse, because that is an I, and the 1 would be an A, so according to Leotta, this will be the choices. Now we need the derivative of that, which I just asked you guys about. It's 1 over the radical of 1 minus x squared. And we need the v, which is just x. So now we know that the integral of the arcsine is going to be u times v minus the integral of v du. Now, of course, whenever you learn a new formula, write it down very often so that you have it memorized eventually, right? So you're doing integration by parts, especially if yesterday was the first time you've ever seen this. Every single time you're doing integration by parts, write down the formula. That way it gets burned into your brain. You will memorize it without having to actually dedicate specific space to it. Okay. All right, so here, all right, Jason is giving us the final answer. Let's see if he's correct. So here, u times v is just going to be x sine inverse of x minus the integral of v du. Just be x over that. All right, so now to compute this integral, I need to, of course, compute this integral. Now, how do I compute that integral? What do we do?
Think about, like, you know, the inverse trig function, derivatives, and integrals. Like, simple as it is. If you were to think about, like, you know, the chart, if you were to imagine the chart, don't look at it, but imagine the chart of, like, you know, of sine inverse, cosine inverse, tangent inverse, and one of them would be the sine inverse, which would give you 1 over radical 1 minus x squared. And therefore, if you were to think about it, like, you know, look.
No, so that's not correct here because there's an x. There's an x here. It's not a 1 over 1 minus x squared.
Well, in this case, but if we were to think about it, look, half sine inverse of x squared. The x squared, take the derivative of it. 2x over radical 1 minus x squared times a half. You would get, like, you know, x over radical 1 minus x squared. So in fact, it would be half sine inverse of x squared plus c.
Okay. Your reasoning is okay, but there's something else I want to try. So again, that's hard to put into words to explain to someone to do that. I think very few students would see things in that way. So maybe going by something a little bit more brain dead or strategic, right? Remember, every time you see a new integral, what do? You go back to the integral strategy. I'm doing integration by parts. I end up with this new integral of x over the radical of 1 minus x squared. How do I deal with that? The moment you are asking yourself, how do I deal with an integral, you start over on the strategy. Step 1 is there a basic rule that can help me do this? Now, Jason's approach is using a basic rule, but it's just not one of the ones I asked you to memorize. So it's going to be kind of confusing to do that. So he actually got through and tried a step 1. However, most people wouldn't see a basic rule being applied here. Step 2 is, can I simplify to use a basic rule? The answer is no. Now step 3 would be, can a substitution work? And so here you'll notice that, yeah, a substitution can work. Substitution would be what we would do here. Let u equals 1 minus x squared. Your du is going to be minus 2x dx. So you're going to have minus 1/2 du is equal to x dx. And so this integral is going to become, and I'm only focused on this right now. This integral is going to become minus 1/2 times the integral of 1 over radical u. And we know how to deal with that. This is going to be minus 1/2. And 1 over radical u is u to the minus 1/2. So you add 1 to the power, divide by the new power, plus c. The 2's are going to cancel. And ultimately now we can get the final answer. This is going to be x sine inverse of x minus, now it's going to become a plus because of this minus here. And then you're going to end up with u to the 1/2.
August
u
or September.
is going to be that.
Yeah. Huh?
Hello? Is someone speaking? Right, so that's going to be your answer. So again, every time you see a new integral, right, go to the strategy, especially if integration is not your forte. I'm kind of giving you a way to streamline things in your head so you have an actionable plan, right? You're never going to be in a situation where you're like, I'm lost, I don't know what to do, right? You're going to know, every time I see an integral, I think about these 3 things in this order every single time. Eventually, by going through the list, you are going to end up with a scenario that's going to work for you. That's going to take the minimal mental effort, where you're not even necessarily going to have to think backwards in your head or anything. But yeah, that's how we would do this. That's the more straightforward way to do it. So that was the integral of the arc sine function. Chat box is in the way. Okay, e to the radical x. Let's do this one. What do we get here? U equals square root of x. What are you doing? You're doing a substitution. Okay, and what's going to happen if you do u equals square root of x? Oh, wait. Just tell me to wait. Okay, so again, going through our strategy. So I would start with a substitution. I wouldn't use the variable u though, and we'll see why in a second. But as Samia has said, yeah, you're going to start off with a substitution and then you're going to finish off with integration by parts. Now, again, when I see this, right? Let's say I didn't know, like I'm totally lost. Like, so for those of you out there who saw this and was like totally lost on what to do. Again, you go through the strategy. You look at it. Does this look like a basic rule? No, we don't have a rule to integrate e to the radical x. Okay, can I simplify this to look like a basic rule? Well, no. How are you going to simplify e to the radical x? Okay, so the third thing you're going to think is, will a substitution work? Now, if you think about what a substitution is supposed to do, some of you might think that a substitution won't work here, because you would realize that if I pick u to be something, I won't be able to find the du. But remember what I told you. That requirement is very loose requirement. It's one that works out in Calc 1 all the time, but in Calc 2, it's not necessarily true. Sometimes a substitution can work even when it's not painfully obvious that it can. So just because you don't immediately see the du in a substitution doesn't mean a substitution isn't worth doing. So how would you know whether substitution work? You still just kind of go through the motions for a little bit and see where you end up. And I'm going to use a different letter for the substitution here, and you'll see why in a sec. Let's say t is equal to the square root of x. Okay. Now, what I can do here is I can square both sides, and I can differentiate both sides. So this is 2t dt is going to be equal to dx. So now I can realize if I swap out the dx with 2t dt, and I swap out the radical x with t, what is this going to look like? This is going to give me the following integral. This is going to give me 2t e to the t. Now, on one hand, that looks like it's a little bit more complicated, but on the other hand, you'll notice that, hey, that's a situation that I do know how to deal with. In fact, our first example was this guy, right? Our very first example with integration by parts was, how do you integrate xe to the x? This is an integration by parts problem. So here you would now do by parts. So by parts tells you that the answer here is going to be t e to the t minus e to the t plus c. In which case you would now have 2t e to the t minus 2e to the t plus c. And your t was radical x. So this is 2 radical x, e to the radical x, minus 2e to the radical x plus c. And that, ladies and gentlemen, is the answer. Okay, so substitution, probably not obvious at this point, but remember, you can always kind of modify your substitution equation, right? So here you start off with t equals radical x, and you're like, well, the derivative of that is going to be 1 over 2 radical x. I don't see the 1 over 2 radical x. It's fine. Rewrite it, solve for dx, plug it in, see what happens. Every now and then you'll realize that the integral that you get by trying that substitution is something that's a little bit more palatable. You can see a strategy that will work here. In this situation, substitution couldn't finish the problem, but substitution got us a good start. substitution put us in a situation where seeing what the next step to do is easier psychologically. Here you would realize that e to the radical x is complicated. The appropriate substitution would be something that takes the power and gets rid of the radical, because I know how to deal with e to a single variable. I do not know how to deal with e to the radical of a variable. So using a substitution, I'm going to get it to look a little bit simpler and then see where I end up. In this case, I ended up in a situation that I know how to deal with. So that is the problem. This is the integral. Boom.
How did you integrate by parts on the t part?
We did it last class, so again, I'm skipping steps. U would be t. So this was the first example we did, so I kind of skipped it. But essentially here you would say u is t, dv is e to the t dt. Which is why, by the way, I didn't use a u substitution in the first part, because if I said u equals u, the u from the substitution and the u from the by parts is different. So I didn't want to mix them up. So I used the t substitution first, so that in my head I could do that. My du would be dt, my v would be e to the t, and I plug that in. Right. But this is a problem that we've done before, so I kind of skipped the steps. And x e to the x or t e to the t, it's one of those things that you do it often enough that eventually you're going to remember what the answer is anyway, without even going through by parts. You'll probably just automatically remember. Oh, the derivative of, the integral of x e to the x is x e to the x minus e to the x plus c. It's something that you'll see all the time. But that's how you do it by parts, and you would end up with an answer like this. Okay, here's another one. Yes, it's very interesting. Maryland. Okay, so ideas here? Integral of
first
x.
start off by seeing if you could apply, yeah.
Right. Apply a basic rule? No, don't know anything like that. Can I simplify to apply a basic rule? No, not really.
Yeah, you would,
Can a substitution work?
Yeah, apply a basic rule and then, no.
Yeah, there's no basic rule for that. Can't simplify that either. So now what? You would think?
You have to integrate by parts.
Okay, grasshoppers. Remember your training. What's the next thing you would think?
Substitution.
Substitution is the next thing you would think. You do not go, your brain should not jump to by parts. Take your foot off the accelerator. It's not a basic rule. I can't simplify it to a basic rule. The very next thing you think is substitution. It is always the third thing you think. Okay, now, if I wanted to do a substitution, what would I substitute? Right, you have to consider the possibility.
Power.
Right, the power makes it complicated, right? Remember I told you guys last time, you would not do x cubed, okay? So remember what makes, so several people thought x cubed would be what you would substitute. Interesting. No, x cubed would not be what you would substitute. You would substitute the x squared. Okay, to recap from Calc 1, you need to remember when you are doing a substitution, how do you make the choices, right? You need to know when you're doing a method, how you actually apply that method. How you do substitution is the following. You need to look at what makes this integral complicated, find an expression that makes the integral complicated, and then remove that expression and replace it with a single variable. Now, if I look at this, what is really making this complicated? It is not the x cubed. Because if I had x cubed e to the x, that's not complicated. I know exactly how to deal with that. That's an integration by parts, straightforward, straight up. right? What's making it complicated is the power of the exponential. Once your exponential power isn't a single variable, it is complicated. So whenever your exponential is not behaving, remember your exponential function is very wild. It grows rapidly, right? So if your exponential starts misbehaving, that causes a lot of problems. The x squared and the power of the exponential is the issue. So if I were doing a substitution, I would do t equals x squared. My dt is going to be 2x dx. So this means that 1/2 dt is going to be the x dx. Now you're going to notice that what I have here is the integral of x squared e to the x squared times x dx, right? My x cubed is really an x squared times an x. Take that x, move it to the last part, and notice what I have here. Here is my 1/2 dt. Here is my t. Here is my t again. Therefore, according to substitution, this is going to give me 1/2 the integral of t e to the t. And there's that guy again. In fact, we know how to deal with that. We would do by parts. And ultimately, we are going to get t e to the t minus e to the t plus c. Now, what was our t in this case? In this situation, our t was an x squared. So this is 1/2 x squared e to the x squared minus e to the x squared plus c. And that is our answer here. Okay. Now, hopefully you guys are starting to see the strategy here. I mean, at this point, we actually don't know many methods. So we're not in a situation right now where integrals are confusing. Just you wait. They will get confusing eventually. They will get difficult. What you need to do is have a way to think about integrals, a way to approach it so that you will know what the right answer is and you'll get to the right answer in an efficient manner. And to that end, I want you guys to be thinking about the strategy all the time. Step 1, does a basic rule work? Step 2, can I simplify it to use a basic rule? Step 3, can I do a substitution? Step 4 is one of the other things. At this point, integration by parts would be the fourth thing. And of course, you have to know when I choose a method, let's say I want to do substitution or I want to do integration by parts. Now you have to know, well, what is the first thing I have to do within that method? So you have a strategy for how to approach the general integral. Once you choose a method to approach the integral, you now need to know what is the strategy for doing that. If you choose integration by parts, the first thing you want to do is find the u and the dv. How do you find that? Leotta. Once you do that, plug it in. When you get another integral, you go through the process again. If you choose substitution, you need to pick who is my u. How do you choose the u? Find the guy that makes the thing complicated. Replace him with a single variable. See what happens. That is substitution. Okay? No, it doesn't matter if you leave the plus c inside or outside the parentheses. Because you're leaving it at c, right? So c is, so a question is, it doesn't matter if I put the plus c inside or outside the parentheses. It does not matter because the c is an arbitrary constant, which means if you're given information to be able to solve for the c, you're going to get the right value that is going to work either inside or outside the parentheses when you start to plug in numbers. Okay.
It won't affect the equation at all, correct?
No, it's not going to affect the answer, right? So this is, for us, it's equivalent to writing 1/2 x squared e to the x squared minus e to the x squared plus c, right? So it's like in this situation, if you took the first one as the answer, whatever answer you got for c, if you had taken this as the answer, you would get double, you would get half of that for this c. So technically, these are two different c's, but you'll find the right value when you start plugging in numbers. So if it's C is an arbitrary constant, it doesn't matter. So yeah, that was that one. Hij. Okay, x cubed e to the x squared. All right, what do we do here?
You set t equal to x cube.
Okay. Set t equals x cubed. So now what do we get for the integral? What does the integral become here? What's the new integral in terms of t?
Oh, 1/3.
Yeah.
T.
Why is
Yeah,
it?
t
Why?
and then.
So notice what we have here, right? It's just going to be e to the t. I mean, where did the other t come from? Right, notice what we have here. We have the x squared dx, right? This part here is that 1/3 dt, right? That's from this. Then we have the e to the x cubed, but the x cubed is t. So we just have e to the t. The x squared dx is replaced by 1/3 dt. So we just have this guy. So this stops at a U-substitution, right? No by parts or anything sophisticated necessary. I just threw that one in there because I wanted to see how many of you would have tried something like an integration by parts and then take forever to actually do it. This is a substitution problem, right? Now, the previous problem and this problem, looking from the outside in, they don't look much different. However, this one required integration by parts, whereas this one did not. Now, it should be obvious to you that the student who would misdiagnose these things, maybe they thought the second one was integration by parts and the first one is only a substitution. Obviously, they're going to get the wrong answer, and they would spend a lot of time before they figure out that they're going to get the wrong answer. So this is why the strategy is going to save you. You need to think in a certain way. It'll prevent you from getting in trouble. So you're going to think, is this a basic rule? No. Can I simplify it to look like a basic rule? No. Will a substitution work? That would come before you do integration by parts or anything else. In this situation, you didn't need anything else. The substitution took care of the problem. All right. So that was that one. It was just a regular substitution. Just me trying to keep you guys on your toes. Okay, radical x cosine of x.
You'll go through the same process again.
Right? Does it look like a basic rule? No. Can I simplify it to look like a basic rule? No. Can a substitution work?
No.
How do you know? If you were to do a substitution, what would you substitute? The radical
Oh,
x.
wait, yeah, substitution will work, yeah. So
Right.
it will be
Now,
radical
looking
x.
at that, notice that what's making this complicated is the radical x inside the cosine. That is super complicated. Here, I would think of doing a substitution. T equals square root of x. That means that my t squared is x. This means that 2t dt is equal to dx. And then I can plug that into the integral. So my radical x is t. And I would have cosine of the radical x, which is t. And then my dx becomes 2t dt. So this is my new integral now. So I did a substitution, and what did I end up with? 2t squared cosine t dt. All right, so that is simpler than the previous integral, but it's not, we're not safely home yet. 2t squared cosine t, how do I integrate that? Well, at this point, it's a new integral. We go through the method again. Is it a basic rule? No. Can I simplify this to make a basic rule? No. Can a substitution work? Well, I already did a substitution, so I already tried that step, and it got me here. It's a little bit better, but it's not finished. So now I need to think about something else. Obviously, at this point, the only thing else we have to think about is integration by parts. So at this point, we're going to be like, integration by parts. Now, once you choose integration by parts, I need to figure out that this is an a, that is a t. According to Leotta, that is the u. Once I figure out the u, now I realize that it's a t squared. That means I have to do integration by parts twice. I don't want to go through integration by parts twice, so what I'm going to do is I'm going to do tabular integration. So I would draw the table, differentiate, differentiate, differentiate. I hit 0, so I stop. On the other column, integrate, integrate, integrate. Then this times that, this times that, this times that, this times that, which is going to be 0, plus sign, minus sign, plus sign, minus sign. This is going to be 2t squared sine t plus 4t cosine t minus 4 sine t plus a constant. And then I just plug in what t is. T was actually radical x. So this is going to be 2x sine radical x plus 4 radical x cosine radical x minus sine minus 4 minus 4 sine radical x plus constant. This is our answer. So that was that one. So boom. And this is the other examples. The next two examples are very similar to what we did before. So in the interest of time, let me just kind of go ahead and you guys can see how to approach these. Hopefully you tried this so you can look through, look over your work and see if you did it. I'm going to do this problem. I'm going to explain to you what I'm thinking when I'm doing the problem so that you know how to think. What do you think about first? Okay, so I see this. Does that look like a basic rule? No. Can I simplify it to look like a basic rule? No, I can't move the x cubed inside the sign or anything like that. And even if I could, that would actually make it even more complicated. Okay, so it doesn't look like a basic rule, doesn't simplify to look like a basic rule. Can a substitution work? I don't know. If I were to do a substitution, what would I substitute? Well, the sine of x squared is the complicating part. So I would want to substitute the x squared. So let's see what would happen if I substitute the x squared. Oh, I can replace the x dx. This integral I can think of as x squared sine of x squared times x dx. So my new integral is going to look like, well, 1/2 dt. That replaces the x dx. That's your 1/2 dt right here. Then I would have x squared sine of x squared, but my t is x squared. So this is t sine of t. And then I'm like, oh, well, that's something I know how to do by parts because it's not a basic rule. It doesn't simplify to look like a basic rule. But this here is an a. This here is a t. So I can do integration by parts. U equals t. Du would be dt. dv would be the sine. V would be the integral of sine, which is negative cosine. And so this is going to be 1/2 u times v minus the integral of v du. This is going to be 1/2. Integral of cosine is positive sine. And that is the answer, but it is in terms of t. So I go back, my t is x squared. So I just come back here and I plug in x squared. And that is our answer. Did you guys follow? Yes, okay, all right, good. And so I was explaining to you what I was thinking. That's how you should kind of think. That's what I expect to go through your head in that order, right? Now, trust me, as a math major, life is fun. Math is beautiful. It's very creative. However, in Calc 2, it's not, right? You don't need to be creative. You don't need to be a genius. You just need to know a certain path, a certain way of thinking. And when it comes to integration, what I'm telling you so far is the way to think. You think this first, you think this second, you think this third, you think this fourth, right? And by just following that strategy, it's going to, you literally follow your nose to the answer. Let's do the other one.
Jhevon?
Yes.
What will happen if you get -1/2 parentheses x squared cosine x squared subtract sine x squared plus c?
That's the same. You just factor out the negative sign. That's the same. You just factored out the negative sign. That's what you did. Right? This is equal to -1/2 of x squared cosine x squared minus sine x squared plus c. If you factor out the negative, they're both correct. There's no difference between those two. All right, let's look at the inverse tangent. So again, I see that, okay, is that a basic rule? No, it's not in the basic rule table formulas. Okay, can I simplify to look like a basic rule? How do you simplify an arctangent? I don't know. Can I do a substitution? What would I substitute? I don't know. The substitution can't work. U equals x is always a bad substitution. I can't do u equals the inverse tangent because then I don't see how to get that derivative in there. So now you start to think, okay, integration by parts. All right, now that I know it's integration by parts, what are the parts? Oh, I only see one function here. Okay, let me create the second function. So this is tan inverse of x times 1. Okay, now I have two parts. This is an a, this is an I. According to Leotta, this is the u. So I would do u equals tan inverse, which now I know how to find the derivative of that. It's 1/1 plus x squared. My dv would be 1 dx. My v is going to be x. Then I'm going to do u times v. Then I'm going to do u times v minus the integral of v du. So now I have this other integral. How do I do that integral? Okay, go back to basics. Is that a basic rule? No. Can I simplify it to look like a basic rule? No. Can a substitution work? Yeah. U equals 1 plus x squared. Du is going to be 2x dx. 1/2 du is going to be x dx. This is going to become 1/2 the integral of 1 over u du. That is ln of absolute value of u plus c. So that is going to be equal to 1/2 ln of 1 plus x squared. Technically, I don't need the absolute values here, but it's potentially wrong if I leave it off, so I'm going to leave it. And so now, ultimately, it's x tan inverse x plus 1/2 ln of 1 plus x squared plus c. And that is the integral of the arctangent function. So hopefully that was...
Isn't it x tan inverse of x subtract half ln absolute value of 1 plus x squared plus arbitrary constant c?
Hold on.
Oh yeah, I see.
That is what I wrote. Is it, oh, you mean a minus?
Oh no, like x tan inverse of x subtract half
yeah,
ln.
it's a minus here.
Yeah, I said subtract half
yes.
ln absolute value of 1 plus x squared plus arbitrary constant c.
Yes. Okay. Last guy of the evening. How do we do this one? So here I'll ask you guys to help me out with this one, just to finish it off tonight with a bang. Looks mighty complicated.
You know what I actually think?
Yeah?
You don't need actually integration by parts. I think we should use like, basic integration formulas, like divide everything, then find the integration, the antiderivatives of it.
Yeah. So you look at that, and you're like, does a basic rule work? No. Second thing, can I simplify it to look like a basic rule? Well, there's just an x squared in the denominator. How about I divide the x squared into each term? By doing that, you would get this. Now can I apply basic rules? Oh yeah, right? That's 1/2 e to the 2x plus ln of x. This guy here is going to be x to the minus 2, add 1 to the power, divide by the new power. And that's your answer. Now, I actually had a student do this using integration by parts before. This was a problem that I put on a previous test. And they took forever to do it because they didn't actually just see, oh, no, you just divide x squared into everything. They thought they did x squared e to the 2x plus x plus 1 all in parentheses. Then they multiplied it by x to the minus 2. Then they did by parts on that. I think they did u equals x to the minus 2 and the dv equals the other part or something like that. This expanded into this whole thing. They took like a page and a half to finish the problem. And at this point, it's like, so, and then sometimes this happens and the student will come, man, Jhevon's tests are so hard. Problem 2 took forever. It's like a page and a half. Blah, 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 blah. And it's like, no, dude, you messed up the strategy. Right? If you follow the strategy, it's a 2-line problem. It's a 1-line problem. But oftentimes students go down the wrong path because they forget to think in terms of the strategy. And it just really causes things to go off the rails. And in the best case scenario, they eventually get to the answer after a lot of work. But in the worst case scenario, they end up getting something wrong. So this was just the last problem. It looks like one of the more complicated problems, but it's actually the easiest integral we did today. Yes, so that was just a reminder. Remember your training, grasshoppers. Right. All right, bye, Maryland. All right, so we're gonna wrap up there today. Tomorrow, So that was tabular integration. That was cool. Hopefully you liked that. Tomorrow we're going to do trig integrals, which is section 8.3. You guys can start reading ahead if you'd like, but we're going to go through that together. But today's lecture on integration by parts and the tabular method is done.
I had something to point out before we leave.
Yes.
Something to tell you. Speaking of our quizzes that we're gonna have next week, are we gonna have a quiz next week?
Yes.
Oh,
and I'll
okay.
give you information about that over the weekend.
Over the weekend, like how we're gonna get set up online.
Right. Exactly.
Do you know what days our quiz?
Oh, it's the first day we come back. It's going to be on Monday.
Monday.
And it's going to cover everything we did this week. So tomorrow we're going to do trig integrals. So your quiz next week will cover everything that we did this week. So you should know about hyperbolic functions. You should know about defining the log as an integral. You should know about integration by parts. Tabular method is optional, but I think it would be nice if you knew it. And you would need to know about trig integrals for the quiz. But yeah, it's going to be Monday. Yeah, practice material for the quiz. Go to the syllabus and do the suggested problems. You can also do the homework for the section that is in Pearson. That's a good practice as well. And if you feel iffy, if you realize that you're still getting a lot of problems wrong, or you're moving kind of slow, or you're still kind of confused, then you go to the textbook and you do even more problems. So that's what I would do. But the quiz next week is going to cover everything that we do this week, including what we're going to cover tomorrow. Yes, it is on Monday. And yeah. All right, so that being said, we are going to wrap up. Thank you guys for joining. Hopefully you had fun. Hopefully you learned. Hopefully you had a good time. I will see you guys in the next one. Be safe. Have a good night, everybody.